This is my presentation on Huffman coding for ITEC 4264 online data structure and algorithm analyst. Now begins the course outline. We have 5 lessons. Lesson one is history, motivation of Huffman coding. Lesson 2, theoretical foundation. Lesson 3, algorithm explanation. Lesson 4, time complexity and analysis. Lesson 5 is real world applications. And then after that, it's going to be a demo code. So starting with lesson 1, we're going to talk about the history and motivation of the Huffman code, as well as the key reasons for its development. History and motivation. David Huffman developed the Huffman coding in 1952 as an alternate to taking a final exam. So he didn't want to take the test. Instead, he chose to write a paper on a problem that was unsolvable at that time. This coding was created to make an ideal lossless data compression method that gives shorter binary codes to repeatedly occurring characters and longer codes to rare ones. At that time, it was like a length fixed coding, so it was just like long, a lot of bytes just to make it. This was made to solve the problem of having an efficient way to reduce data size without losing information, minimizing overall storage or transmission space. Huffman coding has become a fundamental technique used in many compression formats, including zip files, JPEG images, and MP3 audio. And there's a picture of Mr. David Huffman. So, going over the key reasons for the development of this Huffman coding, as I have mentioned in the previous slide, about him choosing to write a term paper. It was a challenge for him to write to solve this difficult problem, which he didn't know at the time that it was that type of problem. He just thought it was just, hey, look, there's a paper to write about. But he didn't give up. He at the end, he was like, hey, might want to get ready for this test. But he realized something that, hey, maybe if I try it this way, it'll work. And hey, building the code from the bottom up worked for him. Another reason is the optimal and variable length efficiency. This code was designed to make the lowest possible average message length compared to fixed length coding. Um, it's a big gap between fixed length coding and the lowest possible average message length. Um, it used variable length codes based on character frequency to save space. The prefix-free and lossless compression is another reason. Prefix means that no coding word has the starting segment of any other code word, and thus allow for instantaneous, unambiguous decoding, as code words can be identified immediately without knowing the end of the full sequence. Lossless compression ensures data integrity, which is vital for text and data storage. Lesson 2 consists of information on prefix-free coding and binary trees. All right. Prefix-free coding and binary trees is part of the theoretical foundation. So prefix codes are code words with no prefix to each other and are variable length, which ensures unambiguous decoding. While the binary trees represents the prefix codes itself, each leaf node represents a code word, starting from the bottom of the tree and going from the root to a leaf node. The code is built for each branch, the root, with the left is equal to 0 and the right is equal to 1. And the characters are stored at the node. An example would be the letter A equals 0, 0, and the letter B equals 0. Um, this will take time to decode because B is a prefix, meaning that they both start with 0. So you have to keep going to make sure that to know which one it is, A or B. Now, if A was equal to 0, 0 and B was equal to 110, then it can be considered prefix free because A starts with 0, B starts with 1. So we know if it starts with 0, it'll be A. If it starts with B, it starts with 1, it should be B between the two. Lesson 3. This is where we get into the explanation of step-by-step algorithm that is involved. We're going to go over the frequency of the analysis of symbols, the building of the Huffman tree, generating the codes, and encoding and decoding. Frequency analysis of symbols. The first step is finding the frequency analysis of the symbol. This requires counting the frequency of each character in the input data. For this example, let's use the input data of abracadabra, which is ABRACADABRA. If we count the characters, we will produce A equals 5, which is meaning that there's 5 A's in the input data. B equals 2, R equals 2, C equals 1, and D equals 1. Next slide, we'll talk about building the Huffman tree. Building the Huffman tree. So we will start with the leaf nodes for each character. As we previous seen, A equals 5, B equals 2, R is 2, C is 1, D is 1. To start the tree off for the root, we're going to take the two lowest nodes and combine them, which is C and D, both equals 1. As you can see on the example to the right, we have a circle representing C1 and a circle representing D1. If you combine them together, you get 2. Continuing on with the tree, we take what we have remaining, the characters we have remaining, which is A5, B2, R2, and the 2 that we got from adding C and D together. From here, we'll go to the next lowest node. And the next one will be between B2 and R2. So we can do either one, but for this example, I'm going to take B2 and I'm going to use that. So you'll put B2 to the right and adding B2 to 2, you'll get 4. Continuing on with our tree, we look at the remaining characters, which is A5, R2, and 4, which we got from combining the previous characters. Now adding R2 to it, left side of the 4, we'll get 2 plus 4, which is 6. Now, the last character remaining is A5, along with the total of 6 that we got from the previous characters. We will add A5 to the left and add that to 6, which gives us 11. And that will be the last node of this tree. Now begin generating the codes. Now we assign the number 0 for the left branches, which I represent left with the capital L, and 1 for the right branches, which I represent right with a capital R. So starting from the number 11 to get to A, we'll go left, and we assign that a 0. Now to get to R, we'll go to the right, then to the left. Data equals 1, 0. To get to B, we'll make a right, another right, and another one right. That's three rights. So that's three ones. As for C, same thing, two rights, then two lefts will give us 1100. And for D, you got two rights, then make a left, then go right. That equals 1101. That's how you generate the codes for that. Now, as for encoding and decoding, if we go back to our previous example of how we decoded the A, B, R, and C for abracadabra, we'll just put in the text like this with A equals 0, B equals 111, R equals 10, A equals 0, C equals 1100, A equals 0, D equals 1101, A equals 0, B equals 111, R equals 10, A equals 0. We're translated by putting all the letters together. And as you count them, you can see that this code is 23 bits long. And if we would have did it by fixed length, it would have been 88 bits long, which would be 11 characters by multiply by 8 bits, and you get 88 bits. So you can see there's a big difference in how many bits it would have been between the two, or how many there is between the two. For lesson 4, gives a brief information on time complexity analysis. Time complexity analysis. The standard time complexity of the Huffman coding algorithm is big O n log n when building it, where n represents the number of unique characters in the input data. For the encoded and decoding, just use big O n, where n is the length of the input message for the encoding and n is the number of bits when it's in the encoded message. For those that know what big O stands for, is the order of, or big O notation, which signifies how the runtime or space requirement grow as the input size, which will be n, increases. Lesson 5 will be examples of real-world applications. Real-world applications. Some real-world applications will be like transmitting facts or text, or using compression formats like PKZip and GZip. Also, some multimedia codats like JPEG, PNG, and MP3. They all use Huffman encoding. I have a picture that entails this through network transmission, file compression, using gzip. All these utilize the Huffman algorithm. So here's the example code output using Java. For this example, we're going to use the letters A, B, C, D, E, and F, and their frequencies will be A5, B9, C12, D13, E16, and F45. And if we follow like we would do for the tree starting bottom, I'm reading from F, C, D, A, B, E. As you can see, 111, we get to E. The code should generate the same. So let's look at it. And already made it. Let's run that. pretty much making the code. Make sure you got the classes for the node and for the tree. You want to make sure you have something representing the frequency. Make sure you know which way to go for the left and right node. You want to index as well and have that data entered for the node. You want to be able to differentiate between the left and the right, which I got L and R for the node. And I got a tiebreaker, meaning that if the left and right is the same, it'll add accordingly. Make sure there's no, oh, we're just going to go left or we're just going to go right. You got a comparison class for each node, A and B. It's going to compare them. And of course, you're going to put them in an array list. And you want to make sure you put down, hey, if you go left, it's going to be 0. If it's going to go right, it's going to be 1. And adding the frequencies to that for total. Running the string, doing the size for the left and right node. And then you want to enter the string A, B, C, D, E, F for the public static void. And we got the frequencies to match. Run the array list that's with S and frequency. Once you get all this, you're going to print it out. And it should match up. Let's run it. And yep. F is 0. C is 100. D 101. 81100. B 1101. And E 111. And that's it.